Good afternoon, everyone. I'd like to welcome you to our webinar today. We'll have two topics for you today. I'll start out with a section on the I-Codes, and then I'll be followed up by Rick Karg from RJ Karg and Associates, and also with Residential Energy Dynamics. We'll be doing a section on the ASHRAE 62.2 ventilation standards and requirements. So first thing I want to just give a quick plug for an upcoming webinar that you folks might be interested in. My colleague Paul Morin will be presenting on Wednesday, April 15th, a webinar on single-family residential air leakage testing. Getting into a little bit more of the nuts and bolts on blower door testing. He'll cover basics of air leakage testing on a single-family home, as well as issues that affect the accuracy and repeatability of tests. So once again, please sign up for that, and I'm sure it'll be a good presentation. So let's jump into it. Today I'm going to be, there we go. I'll give an overview of I-Codes and I-Code status. We'll look at the different versions of the I-Codes, 2009, the 12, and the 15 that tend to be in play around the country. And we'll kind of focus in on the building, air leakage, and duct leakage testing provisions. And we'll look at how some of the individual states, throughout the presentation, we'll talk about how some of the individual states are dealing with some of these new code provisions. Briefly, Energy Conservatory, we are an equipment manufacturer. We make the Minneapolis blower door, duct blaster, and a variety of other products. Myself and Paul Morin are the tech support guys. I'm sure we talk with many of you folks out there. We always enjoy that. But that's our primary function. We're not a testing agency. We're not out day in and day out testing buildings. But in our work, providing tech support to customers around the country, we hear reoccurring issues and concerns that are not addressed in some of these new I-Codes. Just to jump in real quick, some of the key issues that we'd say is that in the 2009 and the 2012 version of the codes that first talk about some of these actual performance testing provisions, there's no citation of a test standard. If any of you have been around long enough, you might be familiar with some of our software that actually has built into it. TechTight software actually has a variety of test standards that you can test to. Historically, most of us grew up, cut our teeth on the Canadian General Standard Board test. That is a multi-point blower door test. A lot of people still use that. Obviously, in Canada, they still use it. Nowadays, we tend to, most folks actually have moved to the ResNet test standard, and the software will have the various ResNet test standards. But the 2009 and the 2012, except for the commercial provisions of the IECC, IECC stands for International Energy Conservation Code, there's just nothing. It basically gives some real brief instructions on how to set up the building and have at it. The 15 is different. The 2015 version of the IECC actually cites formal ASTM test standards. Two standards are cited: ASTM E779, the 2010 version, which is a standard test method for determining air leakage rate by fan pressurization, and ASTM 1827, the 2011 version, the standard test method for determining air tightness of buildings using an orifice blower door. The biggest concern that we have about these two test standards, I mean, these are, if you're an engineering firm, you're going to be familiar with working on these, working with these standards. The commercial segment of the industry is familiar with these two test standards, but these are really engineering documents, and they're I actually found a nice summary. This NTA, it's an organization, it's a third-party independent testing firm called NTA, up on their website. They had a pretty good comparison of some of the provisions of each one of these test standards. So it breaks out current test procedure is really kind of run-of-the-mill. It doesn't really talk about a test standard because the 12 and Minneapolis really, we don't cite standards as of yet, but it compares just a basic blower door test, single point blower door test, to the ASTM E779 that's cited in the 2015 and ASTM E1827 that's also cited. Some of the highlights of this are that the 779 has a requirement that you're going to do both depressurization and pressurization. 1827 would allow you to choose either or. 779 as a one-point test that you can do. On 1827, you can do a single point or a two-point method. Some of the other requirements, really, I mean, for the codes right now, all the codes are requiring is that you calculate air changes per hour 50, ACH 50, CFM 50 times 60 divided by building volume for ACH 50. If you're following these two ASTM test standards by the book, you're going to have to do air density. Nothing wrong with that. Actually, that's something that we'll talk about a little bit later that we do recommend, and that's actually part of the ResNet test standard. So air density corrections, both inside and outside. They'll talk about calculating air leakage coefficients, corrected leakage coefficients, confidence limits. 1827 is looking for dynamic viscosities, and they want you to do an analysis of precision and bias errors for a single or two-point method. Some of the other requirements, they have some requirements for the equipment that's under the apparatus section, how often they want your equipment to be calibrated. Some of the other things, a little bit trickier, under 779, there's a requirement that says the test cannot be run when the product of the absolute value of the indoor and outdoor air temperature difference multiplied by the building height is greater than, looks like 1,180 feet per degree. So there's a on bitter cold, you may not be able to test as per 779. So these are, it's a good first step in that they acknowledged that, hey, maybe we should cite some test standards, but a lot of people feel that it's really, if we look at the training of the force that we have out there, the people that are actually going to go out and do the testing today, now, citing these test standards is going to be problematic for most folks. And the reality is that probably the best standard to cite or to test to would be the ResNet standards. Let's get through that. Some of the other issues that are addressed or that are not addressed in the code, one of my pet peeves is the whole issue of air changes per hour at 50. Whether or not that's the appropriate metric or not, it's what we've got. A lot of people would rather see us use a standard CFM per square foot of surface area of enclosure or envelope. That is the standard that gets cited for commercial buildings, and that actually does get cited in the 2012 commercial provisions of the IECC. So at least the industry has acknowledged that, and we may be moving towards that in the future. But right now, we got ACH 50, and that's normalizing the leakage based on volume. And one of the more important things that anybody's got to do when they're out there testing, we got to know building volume. And the code is silent on how to calculate volume and who has to submit the actual volume numbers. My 2 cents on it is that really that information should be submitted when someone submits plans for approval on new. I mean, these are new construction codes, so someone is submitting. The builder or the architect or the designer is submitting plans for review, initial plan review. And my 2 cents is that should be submitted right up front, that there should be no disagreement, and that information should be readily available to whoever's doing the actual performance test. I think the last thing you guys want to do when you get out into the field is spend an hour plus calculating building volume. And really, because the metric is based on volume, any deviations up or down can affect the outcome of the test. So I'd really rather see that number stated by some other party, and the testers can just go out and do what they do best: get in, get out, do the test. But in calculating volume, again, there's no citation of a way to calculate building volume. ResNet, the ResNet chapter, I'm not sure if it's in Chapter 8, but the ResNet test standard does cite an ANSI test standard for calculating square footages and volume. And ANSI is going to cite Z765 1996, and that you can pull that off a website. But they'll talk about calculation of square footages, and then someone would just have to calculate volume. But if the builders and designers have the prints on CAD files, it's readily available. I mean, they can hit a few buttons, a few keystrokes, and they're going to have that number for you. So if you're going out doing this testing nowadays, that might be, if someone puts in a request, if they haven't submitted that document or that information to the code officials at plan review, that might be a good step to take, is to, first conversation, do we have volume numbers for blower door test? And has someone stated the square footages of conditioned space for each mechanical system? Because that's going to come into play on the duct glass test. So the other key issue that a lot of us feel simply is not addressed in the I-codes is who gets to do the test. There's some kind of breezy language about the code official, where required by the code official, testing shall be conducted by an approved third party. No discussion of certifications, training, whether it's a third party or installers can do it. It's just kind of left out there to the code officials. So one of the things that we have seen, I'm sorry, I'm getting ahead. I'll come back to that issue in a little bit. Let's give you kind of a brief overview. Sometimes we assume that everybody's got a handle on these I-codes. And there's an organization called the International Code Council. I'm not really sure how international it is, but I know it's in play here in the United States. But ICC stands for International Code Council. And they have a family of these codes. And you can jump online. I would encourage anyone that's doing this testing, jump on and get a PDF version of the codes and have at it. But the family of codes would include the IBC International Building Code, IMC International Mechanical Code, Fuel Gas Code, Fire Code, Plumbing Codes. The ones that we're really concerned about are the IRC, the International Residential Code, and the International Energy Conservation Code. Historically, they have been two separate documents, and some of the provisions of the IECC have been incorporated by reference into the IRC. But starting in 2012, the IRC adopted the exact language that's in the IECC. So there is uniformity, and that's a good thing. So by purchasing a copy of the IRC, you will have a standalone copy of the IECC. Relationship between the two, again, IRC really addresses all topics. I guess I would say since 2012, the IRC would address all topics related to residential construction: structural, plumbing, electrical, mechanical. The idea is allows the builder to carry one book. Historically, Chapter 11 covers energy efficiency. IECC, that was, as I said before, that is an energy code. And the IECC will have both residential and commercial provisions. And again, in 2012, the IRC did incorporate the residential provisions of the IECC. The states are free to adopt the I-codes by completely unaltered by reference, and then also modify with state-specific amendments. And these amendments can really help clarify. We'll look at some of these other amendments, but what'll get a little bit confusing today is because states are free to amend as they see fit, the information that I'm presenting is a straight read of the ICC codes. That a state may adopt provisions of the saying they're adopting provisions of the 2012 code, but they may make an amendment. Typically what we see happen, like the state of Illinois adopted the 2012 but they tweaked some of the numbers. They didn't go with the 3 air changes at 50 because it was their first foray into code enforcement with the tightness levels. They changed it to 5 ACH50, and a lot of states are doing that. They're free to do that, and you really, bottom line is, even if you download a copy of the I-codes off the ICC website, you're going to want to get a copy from your state. In fact, some states will actually, you will purchase, you can, in some states, you can purchase your version, your state's version of the codes from the ICC website. So check out that ICC website and see if you can get your own state's version. As of 3/1/15, this is the current status of code adoption in the U.S. And it's a little hard to see some of these colors kind of mesh in there. But we've got kind of a mix and match between the 2015, the 12, the 9, and the 6, and then some states with no adoption at this point, or the code, maybe it's the old, some of the older code that precede the 2006 I-codes. So again, important to find out what's going on in your state, what's going on in your jurisdiction where you do business. Talk to your code officials and find out what they're enforcing and how they're what provisions of the code they are enforcing. Because again, just seeing this map doesn't mean that they're doing a true read on the 2012. It could be 2012 with state amendments. So once again, we've got the 2 code books that deal with energy, IECC, and you'll typically find the residential provisions. The R in the IECC is usually the code for residential. If it has a C, that's a commercial provision. And under the IRC, you'll see it numbered in Chapter 11, and then you'll see sometimes you'll see it in parentheses, the citation back to the IECC. All of this information that I'm going over in terms of code information is available online at an organization called energycodesocean.org or BCAP. This is just a great resource for finding out what code is in play. There'll be links to your state. The Building Code Assistance Project is a great resource for finding out what's going on in your state. It'll have code statuses. You'll find these individual maps, and you can check on that and download all kinds of great information. All right, let's jump into the 2009 version of the IECC. And Chapter 4 deals with residential energy efficiency, and 402.4.1 deals with the building thermal envelope. Talks about the envelope shall be durably sealed to limit infiltration. And there's a key word that kind of pops up that's near and dear to all blower door testers' hearts, and that is air barrier, or in this case, air barrier material. And what is an air barrier material? If you were to turn to, I'll get to that in a second. It talks about sealing methods between dissimilar materials, which allow for differential expansion and contraction, and talks about the following areas that are caulked or gasketed. The code actually lists the actual assemblies in the building that need to be sealed and caulked and gasketed. So it talks about joint seams and penetrations, site-built windows and doors, openings between window and door assemblies, knee walls, under-knee wall bypasses, room joists, other sources of infiltration. This actually comes into play a little bit later because there is a checklist. But back to air barrier. What is an air barrier material? You can turn to the Air Barrier Association of America. Some people say ABBA, some people say ABBA. I'm going to go with ABBA. Air Barrier Association of America defines an air barrier material as any material that has an air permeance of 0.02 liters per second per meter squared at 75 pascals of pressure. And that just happens to be the air permeance of drywall, and it's used as I would say that's used as a control in their test procedure. But that is, if you go to product manufacturers, for a product manufacturer to state that their material is actually an air barrier, it's rated as an air barrier material, That's the nut and bolt pass-fail criteria, 0.02 liters per second per meter squared. Building envelope, the tightness and insulation shall be demonstrated to comply with one of the following options. And one of the two options are, and this is under the 9, you can do a blower door test. There we go. I'm turning my speakers on because Rick Karg has a comment. Rick, you want to chime in?
Oh, yes, Pete. Yeah. There's a question here that I'm looking at, which is a good one, and I happen to know the person who's asking it, so I want to make sure it gets answered. Here's the question. Am I correct that the IRC is only good for 2-family and 3-family?
Yeah, the code, the IRC and IECC will have it's single families, 2-family, under 3 stories, I believe is the actual definition. And I'm not sure I've got a slide on that. I may have a slide on that a little bit later. But yeah, 2-family, is it only good for 2-family, 3-family? Yeah, so the question is, are townhouses covered under this? Is that, I think that's probably what he's getting at, and I have to check on that. So we'll have to come back or get back to the caller on that one. Testing options, 2009 testing options. The air leakage rate initially under the 2009 is 7 air changes at 50, which by any testers and under any metric, most people would say that's not a really tight building, but it's an initial step. It's a first foray into blower door testing, and I guess it was kind of an incremental standard, so that they didn't want to throw 3 at them right away. So under the 9, if you opt for a blower door test, if you're going to do that to comply, 7 air changes at 50. It describes, the 2009 will describe, and actually this language will hold throughout the codes, where they'll talk about, I mean, this is basically your blower door test. This is about all the I codes are going to give you. They're going to talk about basically closing windows and doors. Dampers shall be closed but not sealed, including exhaust, intake, makeup, air, backdraft, and flue dampers. Interior doors are open. Exterior openings for continuous ventilation systems and heat recovery ventilators should be closed and sealed. Heating and cooling systems shall be turned off. HVAC ducts shall not be sealed, and supply and return registers shall not be sealed. Option 2 under the 2009. You can do a visual inspection option, and there's actually a table under this provision that it's a checklist or a table talking about things that need to be sealed and what has to be done. Here's that kicker language: where required by a code official and approved third party independent from the installer shall inspect the air barrier and the insulation. Here is the component, the air barrier insulation inspection and component guide. It'll list air barrier and thermal barrier, ceilings, any dropped ceilings, attic access, knee wall doors, drop down staircases, just a kind of a laundry list of your typical air leakage points in the building. And some of the other guides that are out there will have some pretty good, the code doesn't get into graphics like this, but there's lots of guides. I mean, these are where buildings leak, the likely suspects of where a building is going to have, we call them bypasses, thermal bypasses, anywhere in a penetration in the envelope where air can leak out. It's going to be around plumbing vents, B vents, electrical penetrations, just the normal laundry list of bypasses that leak up into an attic space. Obviously, under knee wall bypasses on some of these buildings can be a big leak, and some more diagrams showing some of these air leakage points, the likely suspects. Under the 2012 version of the code, things got real, and we actually started seeing the metrics change. And under the 12, if your state adopts the complete version of 12, you're going to have language that the building or unit shall be tested and verified as having air leakage rate not exceeding 5 air changes per hour in zones 1 and 2, 3 air changes per hour in zones 3 through 8. And those correspond with this map. These are the climate zone maps under the 2012 IECC. Once again, only in the most southern part of the U.S., down at the bottom with looks like Florida, and probably Hawaii's not on here, but looks like Florida, pretty much zones 1 and 2 in Texas. Anything colder than that, you're going to be in 3 air changes, which is rigorous. That's a good tight building. A blower door test tests the integrity of the air barrier. That's what you're testing. You're testing the leakage rate across the air barrier system of the building. So we can actually draw a line around most buildings and say, here's where the air stops, and also where we typically want those two boundaries. We have a pressure boundary with the air barrier and a thermal boundary where conductive flow stops, and we want those in alignment. If there's a misalignment, our insulation won't perform. If I have an air pathway through my air barrier and my insulation is on the other side of that or deeper into the envelope, I can have issues with the building. So who inspects or tests? Once again, where required, the code official, we're required by our code official, an approved third party independent from the installer of the installation shall inspect the air barrier and insulation. So the authority with jurisdiction decides who tests. That's why it's important in advance of these codes coming into play in your area to find out from your code official who gets to test and whether or not they have any requirements for the tests. Again, the calculation, it's a volumetric based. You're normalizing the leakage based on building volume. Air changes per hour 50 is CFM 50 times 60 divided by volume. And I would recommend getting the volume from a builder or designer. In Georgia, they stepped up and they modified or amended their code. They actually added the requirements or actually a certification. And there's a few states down in the South that have gone. This is kind of a home of South Face Institute, and South Face came up with a certification called DET, Duct and Envelope Tester, and they wrote it in. So in Georgia, you're either a certified DET verifier, or you're going to be a home energy rater, or you're going to be a BPI building analyst. And those are the requirements down there for people to do the testing. So once again, those are the requirements for the state of Georgia. There's South Face. That curriculum, if you're down close to South Face, down in the south, again, I think Atlanta. They're out of Atlanta, but Georgia works with that, and I believe Alabama also recognizes DET. The state of Illinois, they came in and they did adopt the 12 provisions. And they also, I believe they amended. It's not 7 air change. It's not 3 air changes. I think they went with 5 air changes. But they did adopt provisions of the 12. And Pennsylvania came in. They kept it at 7, and they actually cited ASHRAE 119, air leakage performance attached single-family residential buildings. So they cited another test. Again, some of those other blower door test standards: 779, 1827, ASHRAE 119, the Canadian General Standard Board 149. There's a European test standard, EN 13829. That's the passive house. That's used by passive house testers. And then there's ResNet Chapter 8. And basically, blower door test, most of you know. Blower door test, pretty straightforward. Depressurize the building by minus 50 pascals. And then take your CFM at 50 times 60, divide by volume. You got your ACH 50. If your building doesn't pass the test, what do? You're going to have to do, and most of you would need to be prepared to help your builders over the hurdle to find the air leakage sites. And some of the greatest tools you got out there are blower door with infrared. blower door with infrared will show an air leakage pathway. So the hardest part about the about doing the blower door test is when you show up to do the test. If you show up after the attic is fully insulated and everything's all buttoned up tight, if they fail that test and the air leakage pathways are up in the attic, and that's usually where they are. And again, you can use infrared, you can use theatrical smoke, tracer gas, eyes, ears. Let's show a shot of what a building would look like under the naked eye, under visible light. We can take a look at this ceiling, and then if I come in and look at it with an infrared with no blower door, it looks another way. But when I pop on the blower door under infrared, all of a sudden air leakage pathways show up. So this is a great tool to show and document and actually save and work with your builders to show them where their air leakage sites are in the envelope. And but again, if they show up a little late in the construction process, it's going to be tough getting back up into that attic and tromping around in the insulation. So maybe once the air barrier is set, all the penetrations are sealed, but before the attic is blown, maybe that's a good time to do your leakage test and pass your leakage test. Because like I said, once they blow that attic, it's going to be tough. And that's what this attic looked like. There was no insulation up there, and there were some bypasses. You can use little theatrical smoke, little handheld puffers, or larger theatrical puffers. This is a shot of a theatrical fogger with an extension wand used on a commercial building. There's the fogger, and he puts a wand on it. That's Terry Brennan putting a wand on it so he can lay that fog at a key juncture, the wall roof juncture on a commercial building to see whether or not it's leaking air. So, but you can also go old school and rat around in the attic and find those bypasses just by digging around old school, uncovering big bypasses, and those would have to be sealed. That's a penetration in the envelope, electrical penetrations, top plate leakage, all of the likely suspects. Let's move on to the duct sealing sections of the code. Section in 2009, section 403, air sealing the ductwork is mandatory. And for most of you that are in the southern climates, no, I don't have to tell you guys, but duct leakage is a big issue. If you're running your mechanical system either through a crawl space or up in your attic, this can be not just it's an energy penalty. If I'm pumping conditioned air out the top of my building and I have disconnects, that's a big energy penalty. Up in our neck of the woods, we tend to keep our ducts warm, but there's still builders running through the attic. But also, we don't, in Minnesota, we tend not to put a lot of crawl spaces. We tend to have full basements, but in areas where you have crawl spaces, are the crawl spaces vented to the outside, or are they conditioned crawl spaces? All of these leaks can really affect the performance of the building. And there are lots of penetrations. You can go through buildings and find these little air leaks that will add up all through the building, full-blown disconnects, no attempt at sealing at all, and it can cause durability issues. This is a shot from a house in Minnesota that had ductwork running through the ceiling of the the ceiling of the first floor, and they had a full-blown disconnect. So they were pressurizing that ceiling cavity, and there was no air barrier material. They had just stuffed air permeable insulation into that band joist area, and over the course of 10 or 15 years, the condensation was just rotting out the built-right. So you can have hidden durability issues. This building got skinned thinking it was a window infiltration, a window leak issue, and when they got it skinned like that, they saw something else major was going on with the building. So duct leakage in certain climates can have durability issues. And this is a shot from a friend from Montana shared of what happens when you have disconnected ductwork up in a bitter cold climate up in the mountains of Montana. You'll have a complete frost zone. You're blowing conditioned air up into bitter cold, and it can be tremendous problems real fast. So there's two different types of duct leakage tests. You can talk about total duct leakage test, where you pressurize or depressurize. And depressurizing is probably going to get you your tightest result. Not that pressurization doesn't work, but when you depressurize, you're kind of sucking that duct mask film onto the ductwork to help seal it up a little bit better. But it's a little trickier setup. You have to have it's a little bit extra setup on your Minneapolis duct blaster. But both will work, so you can pressurize or depressurize. You're connecting your duct blaster fan to a central return or an air handler, and you're going to pressurize it. You're going to seal the system and pressurize it 25 pascals. The total duct leakage will measure all of the leaks. It's the whole 9 yards. What is the total, both inside the building and outside the building? Duct leakage to the outside, again, can be done either pressurization or depressurization. Same setup, you're going to connect the system, but you're going to need a blower door. And the number that you end up with is only the leakage to the outside. So, pros and cons, total leakage, you can do it at rough in, shorter, easier setup, less equipment needed. The con of a total is that it includes leakage to the outside, so the results are higher, and it might be harder to meet some of these test standards. The outside test often results in a smaller leakage, so it might be easier to pass in some houses. The con, it's longer setup, more equipment, and the building's got to be set up. The envelope's got to be set. So the sections of code that deal with ductwork, 403.2 says that supply ducts and attics need to be insulated to a minimum of R8. All other ducts shall be insulated a minimum of R6. The exception is ducts or a portion thereof located completely inside the building thermal envelope. And so under the 9, you also have to have all ducts, air handlers, filter boxes, building cavities used as ducts shall be sealed. So you got to get out either the foil tape or the mastic. You typically recommend using the mastic, nickel thick mastic, on all of those joints and penetrations. Under the 2009, you can do it at 2 different phases of construction that you're going to verify the tightness either at post-construction, and again, you could use the 2 methods. You could either do it to leakage to the outside or total leakage. And again, this is a strict read of the I code. Your state may have different numbers. That's what a lot of states have done. They tweak these numbers. But on leakage to the outside done at post-construction, 8% leakage rate CFM per 100 square feet of conditioned floor area, or total leakage 12% or 12 CFM per 100 square feet. Under the 9 at rough in, you can your number is 6%. If there's no air handler installed at the time of test, 4%, 4 CFM per 100 square feet. Under the 12, we actually lose the leakage to the outside test. All we're left with is total leakage, and the numbers get real. They get serious. At post-construction, 4%, rough in, 4%, no air handler, 3%. Those are rigorous numbers. And as there's going to be a lot of work working with installing contractors to help them get over that hump. We're in Minnesota here, we're in the process of, actually we're up and running on these new codes, and contractors that are running ductwork outside the envelope may really have some issues passing some of these tests. It's going to be a challenge. But the exception is if all the ducts are inside the conditioned space, you don't have to test. The biggest question is, what is in, what is out? Are ducts totally inside the envelope, or are there areas where I'm running some of my ducts from the inside running out? I think the trickiest questions that we're getting have to deal with bonus rooms, tuck under garages that have a living space above it, or cantilevers, or ducts that run from the first floor to the second floor in outside walls. You really are going to have to work with your local official to come up with guidance on that. In this example, you can see a contractor using some oval duct. Let's see, yeah, there's the oval duct in an exterior wall, but they used R7 foam insulation to theoretically bring that duct inside the conditioned space. But some code officials may not be on board with that, since you don't have full cavity R value in that space. So again, you really are going to want to work with your local official to determine what's inside and what's outside. I think the floor assemblies are even more problematic because you're going to have a limitation on, here's another example, how am I going to get a full R30 into that assembly? Am I dropping the ceiling down? Am I using a combination of materials? Will I ever get an R30 there? I mean, these are really tricky spaces to insulate and to get to perform properly, and the stakes are high. This example, this is again a bonus room from a garage where we're seeing not only duct work but water lines going through these spaces. So how do I protect those, keep them from freezing if somebody leaves the garage door open on a bitter cold winter day? Am I meeting the intent of the code? Conditioned attic assemblies, a lot of questions on those. If you do a conditioned attic assembly, is that volume included in the blower door test? And when I do my blower door test, would the attic hatch be open or closed? Back to the ducts. If you're working with contractors, again, should it be part of your business model to help these partners out there of yours? If you're being brought in to do the test, you got to help them find the problems. Blower door, you're going to use your IR and your blower door. If they're failing their blower door test, same issue with duct leakage. And for years, guys have been using theatrical foggers, injecting a fog. It's a little tricky to use. It's not a solve-all. It's an art working with that. You can overwhelm a room with theatrical fog. We'd recommend that the fogger actually goes to the side of the fan. You don't want to bury it down the center of the fan. It's a glycol liquid, and it's not great on the equipment, but put it to the side and have it drawn from there. But you can overwhelm a space if there's a lot of duct leakage, and really may make it hard. I mean, in this instance, you can see that there's duct leakage in the mechanical room, but where is it actually coming from? I may not be able to see it. So some guys really get good at kind of pulsing it into the system and showing it that way. Another technique, tried and true, using blower door with pressure pans to actually determine whether or not a run is leaking to the outside. That's a great diagnostic tool. And you can use IR in some cases. This is shot from an attic, looking down at the lid, and you can actually, it's old school with black and white, but you can actually see that that things are warm and hot. If you dig out, you can actually you'll have to dig around and actually find the disconnects where the duct work is. Again, some of the other amendments that we've seen out there, back to Pennsylvania, them citing a duct test standard, and actually some new language that's going into play in Florida. They're calling, Florida was citing an ASHRAE standard 152 for duct testing, and then in apparently this year, July, Florida will be adopting some of these new provisions for duct leakage, and they've actually cited the ResNet test standard. And boy, personally, that's really where we'd like to see these things go. Our formal position papers on these topics are that we recommend that in the absence of a standard that you test to the ResNet standard. In fact, the ResNet test standard is based on ASTM 1827. It's very similar, but you couldn't say that it's exact, but it's very, very similar. And my position is that ResNet is actually actively working on, I can't remember if they're trying to get it approved by ANSI or some other national testing standard, but they're working on that, and hopefully we get that taken care of. We also recommend that people doing the test have some kind of training. ResNet, BPI, Building Analyst, Auditor, Infiltration and Duct Leakage Certificate. A lot of the DOE folks out there have the Interstate Renewable Energy Council, IREC, Energy Auditor, and then many people are testing to the South Face DET standard. And so on duct testing, again, same recommendation, follow the ResNet test standard. The BPI analyst may not get you there. So you might need the auditor. I was told there was one other BPI in addition to the IDL certificate that may qualify you to do duct testing. But again, the South Face and the IREC training would get you there. Let's see what other thing. Ventilation. Oh, and so this kind of moves us into the next portion of the webinar today. The I-Code, the IECC, actually in section R403.5 actually says that the building shall be provided with ventilation that meets the requirements of the IRC or the International Mechanical Code. So these mechanical ventilation requirements are actually in the 12. If your state's adopted 12, the provisions of the 12, you may be required to do something with ventilation. And this is a segue into to our section of the webinar with Rick Card. Rick Card, again, was president of Rick Card Associates and Residential Energy Dynamics. Rick's trained as an economist, worked as a building contractor, and has over 30 years experience working with weatherization, home performance contractors, an educator, and consultant. Rick is also a member of the ASHRAE 62.2 Ventilation Committee. Rick, hand it over to you.
Thank you, Pete. Get myself set up here so that you can see my slides. All right, let me go back to the beginning here. I'm going to talk about the ASHRAE 62.2 2013 version of the standard. The adoption of this ASHRAE code is out of sync with the I-codes. As Pete mentioned, there was an I-code family released in 2012 and another one in 2015. The ASHRAE, this ASHRAE standard is released every 3 years also, but the next one will be in 2016. I am going to say a few things about the ventilation requirements of the international codes as I move through this. A little bit about me. Pete already talked about me a little bit, and that's fine. Thank you, Pete. And off into ASHRAE 62.2 2013. This, as many of you know, this standard has been required by the Department of Energy Low-Income Weatherization Program for quite some time. But that is for existing homes. States are starting to adopt this standard for new construction. As far as I know, the state of Maine was the first to adopt it in 2008. They adopted the 2007 version, and I think next came California. And by this time, there are likely to be other states that have adopted this as a ventilation standard. The language of this standard is written so that it can easily be adopted by as a code in a state. The scope of the standard of the 2013 version is that it's single family and multifamily up to 3 stories. It does include manufactured homes such as mobile homes and modular buildings. And it does state in the standard, I'm looking at the 3rd bullet now, acceptable indoor air quality will not necessarily be achieved even if all requirements are met. It would be great if the committee could state that it could guarantee that, but of course that cannot be done. There's so much research that still needs to be done regarding the way different contaminants affect people. We have a long way to go. Basically, there are 2 sections of the standard, basically and very simply. Local ventilation for bathrooms and kitchens. Sometimes people call this spot ventilation, but I want to make you aware that the word spot is not in the ASHRAE 62.2 standard. Local ventilation is used. And then whole building ventilation has another purpose. This is what you size. The local ventilation or spot ventilation requirement for bathrooms and kitchens is prescriptive. The whole building ventilation requires a calculation, and that's most of what I will talk about because that can be rather complex. Let me get my little green arrow here. Why isn't my green arrow coming down? Well, my green arrow isn't working. But the final, the second to the last small bullet, add alternative compliance supplement, that is something that will come up again, and that is only for existing homes. It is not for new homes. There's my green arrow. First of all, local ventilation, bathrooms and kitchens. Bathrooms and kitchens. The point of local ventilation is to get rid of the worst air in the dwelling as quickly as possible. In bathrooms, that is primarily moisture from taking a shower, from bathing. Sometimes smells are in the bathroom also. Those are not considered hazardous, but within the ASHRAE committee, we've been back and forth about requiring the ventilation of half baths where there is no shower or bathtub. At this time, the standard does not require that. It only requires local ventilation in full bathrooms. A full bathroom is one with a bathtub, a bathtub-shower combination, a shower, or a spa. Kitchens, the other place requiring prescriptively local ventilation is important. Of course, the best type of ventilation in a kitchen to get rid of cooking pollutants is a range hood right over the range. Although other types of ventilation in the kitchen do comply with the standard. The prescriptive standards are listed on this slide. First of all, for bathrooms, as I've already mentioned, this is for a full, what we usually call a full bath only. The point is there a shower tub combination in the bathroom? If there is, then these are the prescriptive standards. First of all, 50 CFM demand controlled fan, at least 50 CFM. The ASHRAE 62.2 standard is a minimum standard. If you wish to put 80 CFM in your bathroom for demand controlled, that's perfectly fine. Personally, I prefer 80 CFM because it clears the moisture from a shower out of the bathroom much more quickly. Another option that is acceptable by the standard is 20 CFM continuous. That is, the fan runs all the time. By the way, demand controlled could be just a switch, the 50 CFM. It could be, another possibility is a occupancy sensor. For kitchens, first of all, the more we study kitchen cooking and baking pollutants, the worse they look. I want to recommend strongly that you ventilate your kitchen. Again, the best way is with a range hood. And in new construction, where you're concerned with new construction codes, a range hood is absolutely the best. 100 CFM demand controlled, that is turning it on when you need it, when you're cooking. And I suggest doing this when you're using the oven or using the range top burners. Something that is now developing, and it will hit the mainstream within the next 5 years, I expect, is something called capture efficiency for kitchen range hoods. You can imagine if you are frying fish, if you put it on the back burner and turn on the range hood, it will capture more of the pollutants than if you put the frying fish pan on the front burner. So various fans have different capture efficiencies. Various speeds in the fans will change that. Over my kitchen range, I have a microwave fan combination. That fan is vented to the outside, but it's merely a box over the range. It has a fairly low capture efficiency. And by the way, a recirculating range hood counts for nothing. It must be vented to the outdoors.
Right.
Yes, Pete.
Question, what if the range top and oven are electric? Those requirements apply.
The good question, it makes no difference. The standard, the 62.2 standard, does not distinguish between gas and electric ranges. And of course, if you have a gas range, you have the potential of carbon monoxide, which you might think you don't have the potential of from an electric range, but there are times that an electric range will give off significant levels of carbon monoxide. For example, when you're cleaning the oven with the self-cleaning feature. You can have, I have measured in my own kitchen up to 250 parts per million of carbon monoxide when an electric oven is in cleaning mode. But the standard makes no distinction, and other than carbon monoxide, the pollutants from a range are essentially the same, whether that range is electric or gas. And as I said, certain pollutants like acrolein and PM 2.5, that is particulate matter that's 2.5 microns or smaller that can get into our lungs, these are being discovered as being quite hazardous to us. So it's very important to vent your cooking and baking. This is, I can't hear you laughing, unfortunately, but this is interesting. This is funny. This is a really big screw up. You really have got to wonder how this ever happened. But I want to make sure that you understand that this does comply with the ASHRAE standard. The capture efficiency of this particular range hood is going to be very low, but it does comply with the standard. For existing dwellings, you may use the alternative compliance path. Now, I said that the standard requires 50 CFM in the bathroom and 100 CFM in the kitchen, but if you are dealing with an existing dwelling, there's a section of the standard that allows you to calculate the deficit in a bathroom if it has no local ventilation or not at least or less than 50 CFM, and likewise with the kitchen. And that deficit is then added together, divided by 4, and that amount is added to the whole building ventilation requirement to compensate for the lack of or the deficit of local ventilation. It's called the alternative compliance path. It is only available for new homes, not for existing homes. We'll talk about that again. This is another rather silly diagram with a water heater under the range hood. In the IRC, the International Residential Code 2009, 12, and 15, there are requirements for local ventilation. They're listed here. For kitchens, it is 100 CFM intermittent, in other words, demand controlled, or 25 CFM continuous. For bathrooms and toilet rooms, 50 CFM or on demand, or 20 CFM continuous, which is exactly what the ASHRAE 62.2 standard is. So this is similar to the ASHRAE standard for local ventilation. Well, building ventilation, which is the more complicated of the two, requiring a calculation procedure. Whole building ventilation is intended to dilute the pollutants in a dwelling, from furnishings, from carpet, from people. We all carry around a pollutant plume around our bodies when we walk around the house. You might talk about that with your spouse tonight when you have the opportunity. So the whole building ventilation is meant to bring in outside fresh air and lower these concentrations of pollution. The way it works, this is a preview. We take what's called the total required ventilation rate. I'll show you the table and the equation for that in just a moment. If it's an existing home, not a new home, we can use the alternative compliance path that I mentioned. We are able in an existing and a new home to do a blower door test and subtract an infiltration credit from this simple addition and subtraction, and we end up with the required mechanical ventilation. So, and there are notes down here. There are new building restrictions. You may not use the alternative compliance supplement in new buildings, and the infiltration credit is limited to 2/3 of this initial value, and this will come up again. This is a table that's in the standard, and I suggest that you not use this table because you'll end up with larger values, but it's sectioned by floor area and the number of bedrooms. Here is the basic equation for Q total. This is our starting point. Q, the amount of whole building ventilation, is equal to 3% of the floor area, or 0.03 times the floor area, plus 7.5 CFM times the number of bedrooms plus 1. The number of bedrooms plus 1 is a way of getting at the number of occupants, assuming that there are 2 occupants in the master bedroom and 1 person in every other bedroom. Now for new construction that becomes important because often in new construction you aren't sure how many people are going to be living in the house, but you do know the number of bedrooms. In existing construction, you can, of course, count the number of people to find out how many people are in the house. The requirements for whole building ventilation may be satisfied by operating a fan intermittently. It doesn't have to be on all the time. For example, if you have in your storage room, that is in a box from the manufacturer, a heat recovery ventilator that has a capacity of 150 CFM, and the whole house ventilation requirement is 50 CFM, what you can do is operate this HRV 1/3 of the time. So you operate the HRV on a timer for 20 minutes, that's 1/3 of an hour out of every hour to get the 50 CFM average. That is allowed by the ASHRAE standard. Often when you have very low whole building ventilation requirements, this is a good way to satisfy those requirements.
Rick?
Yes, Pete.
There's a question about, and it's kind of inside baseball, but is there any discussion or rationale for the change in the formula for the required CFM between the 10 and the 13 version? One of the guests is talking about the 0.01 area and the formula for the 2010 change to 0.03 area in the 2013.
Mm-hmm. My guess is that the person asking this question doesn't like me. It's a difficult question to answer, but it's a very significant change in the standard, in the basis of the standard, but it has very little impact on the final result. In the 2010 version of the standard, this number, instead of being 0.03, was 0.01, or 1% of the area. And every house, every single house, whether new or existing, was given an infiltration default, not an infiltration credit, but an infiltration default of 2% of the floor area. Now that went on for a number of versions of the standard, and it seemed rather arbitrary that every house, whether it was built in 2009 or built in 1809 was given the same default infiltration value of 2% of the floor area. So the mathematics of the standard was reworked. We got rid of that arbitrary 2% for default and went up to 3, which actually is where things were anyway, and we made the infiltration credit larger. So now the standard, as of the 2013 version, does a much better job of looking at each structure individually than the 2010 version. I have heard a number of people say, well, gee, this is unfair. Now the ventilation rates for whole building ventilation are much higher than before. That is not true. I've run comparisons on many houses, and for houses in northern climates or moderate climates, you'll find that there is very little difference, 1-2%. You will find differences, however, in warm climates. The ventilation rate, the whole building ventilation requirement for the 2013 version is usually higher than for the 2010 and 2007 versions. So that's a very good question, and it's a very important thing for everybody to understand, that it's merely taking away the arbitrary 2% default that was given to every house and bringing things all up to a level playing field, and then taking care of any adjustments with a blower door test. A blower door test, as I think everybody knows, is based on the tightness of the house. So it's a much better way to do it, much less arbitrary. Good question. The alternative compliance path is for existing buildings only. This was written into the standard in 2010. It's there again in 2013, and it will continue in 2016. If you want to find it in the standard, if you look at a copy of the standard, it's Appendix A. It's for existing homes only, and the primary objective behind it is to make the standard less expensive without sacrificing air quality for existing homes. For example, in the state of Maine, the low-income weatherization program, it'd be pretty tough if you had to install a range hood in every kitchen. Very expensive. It's for existing dwellings only. It looks at the local exhaust requirements of 50 and 100 in bathrooms and kitchens. You look at those. You actually have to measure what the existing fans are, and you establish a deficit for a room. And in just a moment, I'll go through a couple of examples so that you can see what it is. So with this first red bullet, how much less than 50 CFM do we have in a bathroom? Well, if we have no fan in a bathroom, our deficit is 50. The Appendix A in the standard says if you have an openable window, you may reduce the deficit by 20. So if there's no fan in an existing bathroom, the deficit is 50, but then you may reduce that deficit by 20 if there's an openable window, so that would give you a deficit of 30 for the bathroom. Likewise for a kitchen when it comes to windows. You have to measure a kitchen fan if there's one there. Let's say you measure an existing fan and it is 60 CFM. The actual measured flow rate is 60 CFM. There's an openable window in the kitchen. You may reduce that deficit by 20. So your deficit ends up being your deficit ends up being 20 rather than 40. And then you add all the deficits together and you divide them by 4, and you add that resulting amount to the whole building ventilation rate requirement. I will show that to you in an example. There are sound requirements in the standard for if you leave an existing fan in place, say you're going to a house, there's a fan already there, you do not have to worry about sound requirements. But if you are putting a new fan in, the sound, the maximum sound for a whole building fan is 1 zone, and the maximum sound rating for a local fan is 3 zones. If you happen to be installing an inline fan, you might install a fan up in the attic and it serves 2 bathrooms, for example. Inline fans do not have zone ratings because they are installed remotely, and that's fine under the ASHRAE 62.2 standard. So here's an example of alternative compliance. Remember, it's only for existing homes. We have 2 examples. It's a 3-bedroom house, 1,500 square feet. Kitchen, bathroom, here's a bedroom, bedroom, bedroom. Here's a master bath. This is what a window looks like. So here we have a kitchen with no windows and no fans, so the deficit in the kitchen is 100. Here we have a bathroom with no fan and no windows. The deficit is 50. Here we have another bathroom. No fan, no windows. The deficit is 50. We add up the deficits. 100 from the kitchen, 50 from each bathroom equals 200. We divide the 200 by 4 and we get 50. Let's assume our initial ventilation requirement is 75 from the basic equation, Q tote. We'd add 50 to it, and we'd come up with a requirement of 125 for the whole building ventilation. Of course, you can also install fans in each of these rooms. That's fine to do also. Same house, but now things are a bit different. We now have a window in the kitchen, so we reduce the deficit by 20, giving us 80. We have a window in this bathroom, reducing it by 20, giving us a deficit of 30. And in this bathroom, we have a fan that has a measured flow rate of 32 CFM. The requirement is 50. The existing fan is 32, so we have a deficit of 18. There's no window in this bathroom, but if there were, the deficit would be eliminated. We'd have a 0 deficit. So we add the deficits together, 80, 30, and 18, giving us 118. Divide it by 4, giving us 32. And we add the 32 to the initial Q tote, giving us a 107 whole building ventilation rate minimum. The standard allows an infiltration credit for existing and for new dwellings. The new dwelling infiltration credit is limited to 2/3 of the initial ventilation requirement from the basic equation. For the infiltration credit, you must do a blower door test to find out the infiltration, and the standard states that it must be a multi-point blower door test unless the authority having jurisdiction allows a single point. In practice, from what I gather, single point testing is likely to be used. I don't know of many programs that are requiring multi-point testing, multi-point blower door testing. In other words, you would do a test perhaps at 20 pascals, 30, 40, 50, and 60, and then you would chart those or put them into, for example, the TEC software, which runs the blower for you automatically and gives you a multi-point blower door test result. So again, here we have the way you get at the final ventilation rate for a whole building ventilation. We start with the required ventilation, the simple equation of 3% of the floor area plus 7.5 times the number of bedrooms plus 1. We would add the alternative compliance supplement if it's an existing home. We would then subtract the infiltration credit, which for new construction is limited to 2/3 of the total required ventilation, and that would give us the required mechanical ventilation rate, which in the standard is signified as Q fan. Now, in the I-codes, there are some statements about whole house ventilation. In the I-codes, it's called whole house instead of whole building, but it essentially means the same thing. In the 2009 version of the International Residential Code, there's nothing in there about whole house ventilation. But in the IRC 2012 and 15, we have this table, and there are a lot of notes here. This table it's a lower ventilation rate than 62.2 2013. You may operate it intermittently if it runs at least once every 4 hours. And this is also included in the International Energy Conservation Code 2015. Here is the citing of the paragraph. And it's required by the International Mechanical Code 2012 and 15. And by the way, the Energy Conservatory will post this webinar within a couple of weeks, and you'll be able to go there and look at all these slides again if you wish. The International Energy Conservation Code 2015 also gives a listing of the fan efficiency, or sometimes called efficacy, for range hoods and so on. The ASHRAE 62.2 standard does not do this. The ASHRAE 62.2 standard, as part of its scope, does not consider the issue of energy, either fan efficacy or the energy that's used in ventilating a home. Others certainly have looked at that, but it is not part of the standard, the 62.2 standard. Additional selected requirements of the 2013 version of the ASHRAE 62.2 standard. Carbon monoxide alarms are required in every home, whether there is a combustion appliance or not. Every single home. I really like this. I think it's a very good idea. Adjacent spaces, for example, attached garages. This is mentioned in the standard. We don't want contaminants coming from adjacent spaces that might have contaminants in them, such as garages. Instructions and labeling are part of the standard. You must let people know where how to use their system, and you must label the whole building ventilation controls. As far as I can tell, this is not being complied with in most places. I just glanced at questions. Somebody's asking CO detector or monitor. The proper term is CO alarm. So I think the questioner would say that's a detector. So CO alarms are what is required by the ASHRAE standard. Clothes dryer must be exhausted to the outdoors. I think we all know that, but it's been in the standard for quite some time. Sound ratings for fans, I already mentioned these. 1 zone for a whole building. 3 zones for occupant-controlled fans, such as local fans. And when you arrive in an existing house and you're leaving a fan in place, you do not have to worry about the zone rating of those left-in-place fans. Now, I'm going to take a few minutes and go live to a REDCalc tool. You can find these tools. They're free of charge. And the one for ASHRAE 62.2 2013 is online. There's one for 2010. and there's a special one for California. California is on its own adoption cycle, and it's out of sync with the ASHRAE adoption cycle, so their standard right now is somewhere between the 2013 and 2010 versions of the 62.2 standard. So on the Residential Energy Dynamics website, there's a special ASHRAE tool for you folks that are working in California. This is what the tool looks like, but I'm going to take you live briefly just to show you that. You should be able to see the tool on your screen now. And again, these are free. You can choose existing or new construction. Now, if I choose new construction, the tool, you can't really see it, but it's collapsing. The sections of the tool that are not allowed for new construction disappear. So I'll go back to existing, and you can choose your weather station for North America. There's also Canada. About 1100 TMY3. TMY is typical meteorological data. There are about 1100 for North America. With the tool, if you have a question, you can click or touch any of the labels or results, and it will give you pop-up help, and you can get rid of it by touching or clicking on the X. And you can also change units. You can change them on the fly, or if any of you are listening from Canada or Europe or any other place other than the US which uses the metric system, you can go to the preferences and change all of your units to the metric system in all of the tools. So I have pre-filled this: living area 2,100 square feet, number of occupants, the building height. The house is in Denver, Colorado, and it's a fairly tight house, 1,200 CFM 50. There are, you can use the advanced blower door units. We will be bringing this up to date to the ResNet model. As Pete mentioned, he talked about the ResNet model. This is close, but it's not there yet. But you can adjust for temperature and altitude and pressure exponent. Notice here the measured leakage was 1200, but because I've adjusted it for altitude and temperature, it's 10 degrees outside. Notice that the CFM 50 used in the calculation is lower, 1115. However, if I unclick Use Advanced Blower Door Inputs, now the calculations will use the 1200. If I click it again, now the calculations will use the 1115. There is a section here for existing homes. At the top of the tool, if you choose New Homes, this section won't even show up. It will go away. That is this one right here. Use local ventilation alternative compliance. I've filled this in a little bit. These would be the measured values here. And you checked whether you have an openable window or not, and this is the total deficit right here. I'll just leave that checked. If I uncheck that, then that does not figure into the calculations. So now down to the final results here. These are the results. The effective annual average infiltration is 48. That comes from your blower door test. The total required ventilation rate, that's Q tote, is 93. Alternative compliance, that's for new construction, that gets added to the 93. And then the infiltration credit gets subtracted from it, so we end up with a total requirement of 58. Now if I deselect the local ventilation requirement, that value goes away and this number comes down. And there are a couple of other things added to the tool. For example, if the capacity of your fan is 80 CFM, right here, this will tell you, it's looking at the 45 right here, this will tell you if you want to run it intermittently, it must run 33 minutes every hour at 80 CFM to get the effective ventilation rate of 45 CFM. In this bottom section of the tool, I'm not going to go into right now. That ends my prepared presentation. If there are questions, Pete, you can give me questions and I'll do my best to answer them.
You bet. Rick, we've got one that goes back to the kitchen. And the question is, when new buildings have an open floor plan where the kitchen is open to other living areas, how is kitchen volume calculated to determine the ACH?
That's another challenging question. This question was asked of the ASHRAE committee. Anyone can submit an interpretation request to the ASHRAE committee, and the committee must, by ANSI regulations, respond to that. The committee responded to this question, and our charge is to respond to interpretation requests in the manner in which we think the standard was written, the spirit of the standard. And the response to that interpretation request, this was about 2 years ago, exactly the same question. This has to do with the 5 air changes per hour for the kitchen. It's either 100 CFM on demand or 5 air changes per hour running continuously. If it's an open kitchen, the ASHRAE committee decided that you would therefore have to include the entire volume of the house for your calculation of 5 air changes per hour. You might very well end up with a very large number, leading you with the opinion that it would be very unwise to run the fan continuously. It would be better to run it intermittently. Good question, and I can say with authority because this was an interpretation request 2 years ago, and the committee did decide that the entire volume of the house would have to be used in the ACH, the 5 ACH calculation at that time.
Great. Rick, can you comment on, apparently someone's having issues with code officials, authorities having jurisdiction, and an issue with window credits being subjective to their own policy?
Well, that of course can happen, and there is so much these days for code enforcement officials to keep track of. I know in the state of Maine we've got, if you just look at the codes we follow, if you stack them up, it just in the number of pages, it's about 6 to 8 inches thick. If you stack it up, that's a lot for a code official to know. If you are following the ASHRAE standard, Appendix A states clearly that if it's an openable window on a bathroom or a kitchen, that you may reduce the deficit for that bathroom or kitchen by 20 CFM. It's very clear in the standard, and it does not say there that it's up to the authority having jurisdiction, as I recall. So that's a fairly clear issue in the standard. Now, years ago, for I'm guessing decades, it has been in various codes, BOCA codes going way back, that if you have an openable window in a bathroom, you do not need to put in a fan. That's where we were once. That has now changed, and I think the change is a positive change. But some code officials are still thinking about that and might remember hearing an openable window does not qualify anymore as for ventilation of a bathroom. But the ASHRAE standard 2010 and 2013 versions, Appendix A, does give you give it 20 CFM credit for an openable window.
Sounds good. Rick, here, I think this is probably, this is a good question. This may take some time, but so the question is, how does this vent calculation, and I'm not sure if they're referring to the software or just 62.2.13 in general, compare to that put forth by Building Science Corp?
I think I can answer that pretty quickly. Quite a few years ago, Joe Stebrick of the Building Science Corporation published his own standard. I took issue with that. Joe Stebrick was not on the ASHRAE committee then. He was before that, and he's now on the ASHRAE committee again. He called his document a standard, but a standard is only something that has been accepted going through the right channels. It's an ANSI procedure. The ASHRAE standards go through that procedures. They are officially standards. The I-codes go through that procedure. Joe Stebrick's document did not go through that procedure, so I always objected to him calling it a standard. I think it was a good document. He took issue with some of the ASHRAE ventilation rates, and some people listening might have been at Affordable Comfort last year in Detroit, where there was a ventilation panel, the Great Debate, and he was there, I was there, and about 5 or 6 other ASHRAE 62.2 committee members there. A big problem that we have that I mentioned earlier with the ASHRAE standard and with Joe Stebrick's document, is that we don't have enough epidemiological studies to really know what the ventilation rate must be. We're doing the best we can, but we need a lot more information. Not only is the ASHRAE committee missing that information, but so is Joe Stebrick. He's back on the committee now, and he is, which I think is a good place for him to be. I think what he's doing is more positive. And the standard is changing. It's making some significant changes, not only because of Joe Stebrick, but because of many others on the committee. So those listening should understand that the Building Science Corporation ventilation standard, as it was called, is not a standard. I know of no jurisdiction, no state, no municipality that has accepted that as a standard. And they would have, there would be no way for them to justify doing so. Anybody listening could write a document and call it a standard, and it would have no more or no less validity than what Joe Stebrick did. He did get it out there, though, and that was a good thing. He started discussions, and I think those discussions were important. And I want to also say in this vein that anyone listening can submit a change proposal for the ASHRAE 62.2 standard or an interpretation request. It's open to everyone. You go to the ASHRAE website and find the appropriate forms. You submit those, and the committee is obligated to consider your proposals or your interpretation request.
Rick, are the REDCalc tools available for Android device?
Good question. The REDCalc tools will work on any device that has a browser. They will work on your computer, on your iPhone, your iPad, your Motorola phone, Android phones. All you have to have is a browser, and they will work. They are web-based software. They are not native apps. So we don't have to worry about having an iOS version and an Android version. And by the way, there is, you notice up in the top here, there is a print function, and it'll give you a nice clean print on your computer. But if you're using a smart device in the field, a mobile device, a phone or a tablet, all you have to do is take a screenshot of the tool. Your device will automatically send that screenshot to your photos, and you can later, you can then email that photo, that screenshot, or text it, or print it when you get back to your office.
Sounds great. I think we're just about. Is anything else? Any closing comments, Rick?
No. Thank you for the opportunity to present this. We had a good turnout today, and I appreciate it. Pete, thank you for what you did.
Well, thank you, Rick, and thanks to all the participants. Great questions, and hopefully folks come back for more of these. These are great forums for us. Thanks very much.
Thank you.
Bye now.